everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were looking at proper motion, the motion of the stars through the sky that's not dependent upon the Earth's motion around the sun, and that's what we call proper motion. But there's other really interesting things that we get from straight up amateur observing of the sky. If you actually look out with a small telescope or binoculars, you find one of the more interesting little wonders of the night sky is that sometimes two really bright stars are very, very close together as seen through binoculars. But in the sky, they look like one star, but together, when you look at them through binoculars, you can resolve the two stars, and they're called binary stars. So binary stars are a really interesting set of things, and they're subject of massive amounts of study and research because they can tell us a huge amount about the nature of stars. And by the way, they're really pretty to look at. So if you get a chance to go to some amateur club or something like that, or get out in the deep woods or something, take a pair of binoculars or a small telescope and go take a look at some of the prominent binary stars in the sky. One of them is Alcor and Mizar. And Alcor and Mizar are the middle star in the handle of the Big Dipper. And if you look really closely at Alcor and Mizar, you can see that one of them is pretty dim and one of them is really bright. And that's a classic visual binary. And if you look closely at Mizar, which is the bright one in this image which has been derived from the Palomar Sky Survey, then you'll actually see that Mizar is actually a binary itself. And so when you look at it in a small telescope, you actually see that. But in this image, they're too close together, they get washed out, and you can't see it. Anyway, so apparent binary stars are stars that just happen to be in the same direction. And sometimes they can be very, very distant, very, very far apart. Other beautiful pairs of apparent binaries such as Nu Draconis. And I believe Nu Draconis is a beautiful actual binary, but this is definitely one of the prettier binaries in the sky. This was taken by David Ritter, and I believe this is also from Wikipedia, but David Ritter took this great photo of this wonderful binary. And sometimes these are called the cat eyes because if you look at it through a telescope, there's pretty much not many other really bright stars in the field. And so they look like little eyes staring right back at you. And that's called Nu Draconis, one of the nice binary stars of the sky. One of the classics of all of the stars of the sky, all the binaries, are true binary stars, such as Albireo. Albireo is Beta Cygnus, and it's halfway between Vega and Altair in the sky, right along the Milky Way. And that's why there's so many stars in this image, is because from the Palomar Sky Survey, we see that since we're looking along the Milky Way, we see a huge number of stars in the middle. And that's something you can see if you go somewhere dark. But Albireo is really wonderful because you get a really gold star right next to a really blue star. And as we look out in the sky, we find that a lot of stars are it's pretty common for them to come in binaries. And then when they're orbiting, when they're true binaries, not just apparent binaries, but if they're truly binary stars, then they actually orbit each other. They orbit a common center of mass, meaning then one star doesn't just orbit the other like the Earth orbits the sun. No, both of them have such a great enough mass that the center of that mass, the balance point between the two of them, is not inside either star, but maybe halfway between or 3/4 to the way out for one, depending on the masses. But about 60 to 70% of all the stars in the entire sky are actually two or more stars. So most stars are binaries, which is really interesting. So when you look out in the sky and you see all these stars, most of them are binaries, which is pretty cool. And another great example of a binary star that you can see very easily is the brightest star in the sky, Sirius Alpha Canis Majoris. And Sirius has a very, very, very dim companion. It can only be seen with large telescopes, and it's very close to the star. In fact, this image for the Palomar Sky Survey, it's actually too bright. It's washed out its companion star, so you don't actually see the companion star in it. But let's take a closer look at this particular true binary star. True binary stars are gravitationally bound, and the gravity between them will determine how they move. And so this is yet another aspect of the motion of the stars. So proper motion is the motion across the sky, but then there's an effect of the space motion as it moves. Maybe in addition to proper motion, you actually see the stars actually orbiting each other. And if you could actually orbit each other, then you could measure then you know they're at the same distance. So then if they're orbiting each other, they're at the same distance, You can figure out how far apart they are. If you can figure out how far apart they are and actually get their orbit, well, then you can use Newton's law to determine their masses. So now this is telling you about the physics of the stars themselves. All right, so the types of binaries that you actually see that are actual true binaries, not apparent binaries, but true binaries come in three basic classes. One is a visual binary. You can see both stars and follow their orbits with time. And so a visual binary is definitively something you can get inside a telescope. And you can make both stars out. And Sirius is one of the most important examples of such binaries. Eclipsing binaries are interesting. They're so close together that we can't see them as separate stars. But interestingly enough, if you watch their brightness over a period of time, you'll actually see them get brighter and dimmer and brighter and dimmer when one star goes in front of the other and blocks some of its light. And when that happens, you get an eclipse, and that eclipse is strictly dependent upon the location of the star in the sky, and that eclipsing binary star then dims in a particular way. And that's the classic example is Algol or Beta Perseus is one of the classic examples of that. That's been known since antiquity. That's why it's called Algol, which means the winking demon. So even the ancient Greeks knew that Algol was a blinking star. And finally, what you have is a spectroscopic binary. They're too close, again, just like eclipsing binary, to be seen as separate stars. But you can detect their orbit by looking at Doppler shifts of their spectral lines, and Gamma Cassiopeia is an example of that. All right, so let's go back to Sirius. What's fascinating is that people have been watching Sirius through telescopes for a long time, and so for about 100 years, people have noticed that Sirius A, which is the bright star, and Sirius B move together through the sky. And Sirius A doesn't move as much as Sirius B. And Sirius B is a white dwarf star. And Sirius A is, I believe, an A-type star. And they're all very, it's a much brighter, much more massive star than the white dwarf that orbits it. And notice they have these funny kind of circular orbits. They orbit a center of mass, which is at the center of this diagram. So you got this kind of plus sort of shape, which shows where the center of mass is, where the two straight lines converge. And the orbits of the stars orbit that common center of mass. And the reason it doesn't look centered up to us is because the orbits are inclined with respect to our viewing of them. So they don't match up that, but that's exactly where the center of mass actually is. So they orbit that center of mass. So when one star is far, the other star is far, and when they're near, they're near. So they trace the same location in this. They go from the outer portion when they're very far apart to going very close together. So they go far to no close to far to close. All right. So what I did is I decided to use a nice little tool called SkySafari to actually show you the orbit. So now unfortunately, SkySafari centers on a particular star. So what I'm doing is I'm actually just showing you the orbit of Sirius B, the white dwarf, with respect to Sirius A, the bright star in the sky. So you have Sirius A there, and we see over time, as you look at the time that's passing on this thing, we're now almost 100 years in the future, and so it orbits quite quick. It takes a long time for it to orbit each other, and we can see there they go orbiting, orbiting, and orbiting. But as we zoom out and look at larger and larger areas of the sky, we see that once your field of view is typical for a large telescope, or with a standard eyepiece, which is about what we're looking at now, it's hard to make out the binary pair. Okay, so now what we can do is we can go faster in time, actually turn off the double star, and we'll just see exactly how Sirius moves in the sky. Last time we talked about proper motion, so now let's actually show what that looks like. So the grid I'm turning on here is the coordinate of equatorial coordinates, which is with respect to the Earth's equator and the North Celestial Pole. So that was a little bit busy, so I turned it off. And now what I did is zooming out to show you the proper motion of Sirius. Now what I'm going to do is actually go much faster in time and see how we look. So we'll zoom in a bit more. I'm not really sure what I'm doing here. Okay, let's go click around here. Let's find out the constellations, because now if we check out the constellations and look at the boundary lines of the constellations and the traditional lines that we see in the constellations themselves will change over time. And this is too busy, so I'm just going to dim some of the stars so we only get magnitudes down to 6, which is typical for like a really, really, really dark location. So magnitude 5, which is not so dark. Now I'm going to actually speed up time again And as I speed up time, I'm going to change it from 24 years to time. Now we get the effect of all of the changes of proper motion. You can see the years going by rather rapidly. We'll turn off the planet so we can actually see what's going on. And you can see the years are now 14,000 years in the future, 15, 16,000, 17,000, 18,000. And we can see the proper motion of Sirius across the sky with respect to all the stars in its background. And that's because Sirius is quite near to us, only about 7 or 8 light years away. And as such, it moves quite along really quickly, just like Procyon does, that's sneaking into the picture over there. So that gives us a little bit more about the nature of all these stars and their positions in the sky, and specifically one of the most important binaries, Sirius A and Sirius B. So we can then reduce the motion and then make a graph out of what we see, and we reduce it so that we only worry about the motion of Sirius B with respect to Sirius A. And so we center it up, and we see that it takes on the order, what do we got there? Approximately 1991 all the way through, oh my goodness, 1969, 73, 60. Takes about 50 years for it to go around in one orbit. And that orbital time frame is about 20 or 30 arc seconds across. So you do have to have a very high resolution in order to see them and split them. But if you have a large telescope and you're using, say, a 17 millimeter eyepiece or a 12 millimeter eyepiece, you should be able to split the two stars. But Sirius B is very, very dim compared to Sirius A. But this is called a visual binary. So you can actually track them, which allows you to actually use Newton's gravitational law at Newton's laws of mechanics to actually get the masses of both stars. Measuring mass is really important because mass is one of the most fundamental measurements we can make of anything. And so mass determines gravity and the gravitational pull on it, and it determines your weight. How much mass you have determines your weight on Earth. And so the Earth's mass can be determined by the motion of the moon or by satellites in orbit. And the sun's mass is derived from the motions of the planets. And all other stars' masses are based on the fundamental fact that you have to see their effects on companion stars. So if you take stars like Sirius, you can hopefully derive something from Sirius A and understand that kind of star, and then apply what you know to other kinds of stars. So the only kind of star that you can actually get that derives directly their masses is from visual binaries. All the rest are much more difficult. Visual binaries are the most important, and they're usually near enough. You can get parallaxes, and then if you can get that, you can get a real physical separation, and that gives you exactly what you're looking for, which is a map or a catalog of stars of known masses. And so the Washington Double Star Database, which is maintained by the Navy, the U.S. Navy, which is really interesting that they do that, maintains a massive database of double stars. And all sorts of data points are given by various researchers, and they maintain this database to try to see what's going on. So here's an example of one of them, and its label is there, WDS 1805 1223 Well, that would be something you would see in the database. And so this is a well-made map of a binary star. How do you get the mass? So if you have them, you can think of it as balancing on a little teeter-totter. So put that little black triangle in the middle, and so there's separation. If you can get their physical separation and determine their center of mass, then the ratio of the masses equals the inverse ratio of their distances from the center of mass. And the distance between them is the sum of just the two of them. So we've got this A, the total A is the distance between the two stars, M sub 1, star 1, and M sub 2, star 2. And A1 and A2 are simply the distances to the center of mass, which is the fulcrum point. So you can just imagine that they'd be perfectly balanced on a big, 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 long stick like that. So the fat one has to be close to the center, and the little one has to be far away in order to balance it. So that's where you have the ratio of the masses is equal to the inverse ratio of their distances from the center of mass. So if you can determine their distances, their absolute distance, and determine where the center of mass is, then you have the ratio of the masses. You know how, and that's a very easy calculation because that's just distance. That's their distances. How do you get distance? You need to have parallax. If you have parallax, you can get their relative distance between them. So now you have the ratio of the masses. How do you get the individual masses of stars? Well, it gets tricky. If you measure the period of the motion, and then you measure the semi-major axis, which is how far apart they are at the greatest distance, or their average distance between them. And then you can solve Newton's form of Kepler's third law to get the sum of the masses. So you can look at their separations and get the ratio of the masses, and then you can solve this equation to get the sum of the masses. And if you have a ratio and a sum, you've got two equations and two unknowns, and so there you go. You can solve for the individual masses. But you have to accurately measure the period of the rotation, you have to accurately measure their distance between each other, and you have to accurately measure where the center of mass is. And once you get that, then you can get the individual masses of stars. And that means you got to take up a lot of time and a huge amount, and you have to know the distance. If you do not know the distance to the star, then the distance between the stars will be a mess. So a little tiny distance error makes a massive error in the mass. So you got to be really, really careful. And so getting the actual distance in terms of the astrometric distance with parallax is critical. So parallax distances are incredibly important for all of astronomy and the physics of stars. And it all begins with these visual binaries. So the massive Sirius B, which is now visualized in this Hubble Space Telescope image, is being shown here. And Sirius B is a little tiny star. It's known to be about 12,000 kilometers, or a little bit smaller than the Earth. And it's a little tiny thing. And so we have Sirius A, which is really, 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 really bright in the center of the field. And then there's this little tiny dot to the lower left, halfway down at about 8 o'clock on this image of the Hubble Space Telescope. And this Hubble image shows, there it is. And so it's a little tiny thing, and it's a very, very small radius star. And we'll get to how we get the radius later. But we've learned that the mass is about the same as the sun. But the size of that star is a little bit smaller than the Earth. And you can actually where the Hubble Space Telescope did is they looked at the redshift of light coming off of the white dwarf. And this is what is called a white dwarf type star. And the redshift of the light coming off of there is gravitationally shifted, as we saw in one of my earlier videos, that gravitational redshift can occur, and it's the loss of energy of light as it comes from the surface of something, even the Earth or the sun. But with a white dwarf, it's measurable. And so we can actually measure using the redshift of the light coming off of the white dwarf that it has just about the mass of the sun, but the size of the Earth. So it's an incredibly tiny, massive object. So spectroscopic binaries, but most binaries are really just too far away to see stars separately. That's unfortunate, but we don't have a lot of close stars, but if we did, we'd probably have problems of a different kind. We have comets falling in and dinosaurs being killed all over and over again and so forth. And there's all sorts of stuff about that. But in any event, you can detect the orbital motion of stars by looking at the Doppler shifts, the periodic Doppler shift of the spectral lines of the stars themselves. And that tells you from the Doppler shifts, that can give you the period, the orbital period, and it can give you a rough guesstimate of this and give you a size and the pattern of the orbital velocities. So if one of the sets of lines is moving small, then it's not being shifted as much. That would be star A in this diagram. And star B, however, would have a big shift. And so that big shift would mean that it's a less massive star. And the ratio of how much they're changing is the ratio of their masses. So since you can't see them, you must estimate the semi-major axis from the orbital parameters derived from the spectral Doppler shifts. And the real problem is you can't tell the orbit is tilted like you can with, say, Sirius. So you have to know the distance in order to get the semi-major axis estimation. All you can get is the semi-major axis with a little bit of inclination. So that's one way to get really close to getting masses with the spectroscopic binaries. And the shift is more detailed here. We can see that one of the stars is shifted left and one of them is shifted right. And sometimes you only see one of them. Maybe one star is simply too dim in order to be seen. And so you just see it shifting back and forth and back and forth and back and forth. And that's called a single line spectroscopic binary. And that also occurs. So let's look at a real big piece of data. And this is from 2013, published by R.F. Griffin in the Astronomical Journal. And these are radial velocity measurements of an actual spectroscopic binary. So we looked at a particular wavelength of light and then saw how what the radial velocity is for that particular wavelength over the course of time. And notice that it's not just back and forth, that there's a distinct curve signature. And you can use the curvature signature to determine orbital parameters even more. This radial velocity measurement carries a huge amount of information, but the most important information that it carries is mass, because you want to be able to derive the mass of that star, because that gives you the fundamental physics of the star. And that's what we're really after in this thing is, why do we want the mass? Because that tells us something really interesting later. But the measurement actually, the interpretation of this curve such that you can get the mass of the star is a real work of art. So you can go look at his paper if you want to, and it's on archive or whatnot. I'll put a link on YouTube. So we're going to apply this to a particular star next time when we talk about the incredible discovery around the nearest star to us, which is Proxima Centauri. Proxima Centauri has been found to be a binary, but of a different kind. So Alpha Centauri is a two-component system. It also has a third component named Proxima Centauri. And we can see Proxima Centauri highlighted in this image, but they're gravitationally bound, and Proxima Centauri is the nearest star to us, other than the Sun. And it's an incredibly far location, like almost 4 light years, just under an arc second of parallax. But it is a pale red dot. And so this pale red dot becomes an incredibly important thing for us to study for a lot of reasons, which I'll get into next time. We'll see you soon.